So thanks, John. Thanks for the organizers for this great meeting, for inviting me to talk about galaxy formation from redshift 0 to 2, or redshift 0 to sort of the phase in the universe when the universe was most active. So we've seen this plot before by, how does this work? Is there a laser here as well?
Yes, the green.
Okay, so we've seen this plot before by Peter, who actually showed the star formation history of the universe. And what you indeed see at this redshift range around the redshift of 2, that the universe is forming most stars, and also actually most of the black hole mass is formed at that time. And then you see this nice decline over here. So the universe is becoming less active from a redshift 2 to a redshift of 0. So how does the universe at a redshift of 2 actually looks like? So this is to give you sort of an idea of what type of galaxies we're actually finding at a redshift of 2. So this is quite of an old plot, so there's not that many galaxies. But here you see the rest frame color on the y-axis, so the age, and here you see the stellar mass. And the galaxy distribution at that time is already nicely splitting up into two populations. So we already see the elliptical galaxies that we see today, so these galaxies that don't have a lot of star formation anymore. But we also have these star-forming galaxies which have more like irregular morphologies. So if you follow the galaxy distribution throughout with redshift, you find that the galaxy distribution is actually split into quiescent and star-forming galaxies, even up to about a redshift of 2.5. Okay, so what are we looking at here? So this is a plot that almost everyone uses nowadays to discriminate whether a galaxy is actually star-forming or quiescent. So you see there's no mass in here, there's just two colors. So on one hand, there's U minus V color and there's V minus J color. So if a galaxy is red in U minus V, it can be either old, and then it falls in this box, or it can be red because it's dusty, and then it falls on this sequence over here. So by having these two colors, you can really discriminate whether a galaxy is old because it is red because it's old, or red because it's dusty. So this is a very powerful trick to really split the galaxy distribution in the star forming and in the quiescent population. So you see that out to a redshift of about 2.5, you find galaxies in both boxes, and maybe even higher, you already find quiescent systems. So how is the stellar mass being built up? So this is the, I think, the state-of-the-art mass functions, only published this year by Adam Mazin. This is based on the Ultra Vista survey. And here you see the mass functions of galaxies, of all galaxies. And here you see the different redshift bins. Here you see the quiescent galaxies, and here you see the star-forming galaxies. So it's split using that color criteria that I showed you on the previous page. And what you see is that both the star-forming population are building up their stellar mass, or building up, and the quiescent galaxy population is building up. Okay, so this is what I think we've been doing in the past years. So what have people in the field of galaxy evolution from 0 to 2 been doing? Well, lots of people have been working on this star-forming main sequence that Dan already talked about. So this is the sequence between star formation rate and stellar mass, on which most galaxies seem to fall, who are forming stars. So lots of people have been working on how do we actually go from a star-forming galaxy to a quiescent galaxy. So how do we actually stop the star formation in these galaxies? And then there's a group of people who have been working on this last question. So what happens to quiescent galaxies after they become quiescent? So we saw that there's already a lot of quiescent galaxies at a redshift of 2. But interestingly, these systems are not the same as the early type galaxies in the local universe, because they're much more compact. And something needs to happen to them so they get bigger and puff up to become the elliptical galaxies in the local universe. Okay, let's first go to the star-forming main sequence. So this is a different plot. So this is lower redshift than what Dan talked about. So this is up to about a redshift of 2.5. Again, you see the star formation rate versus stellar mass. This is lowest redshift, up to 2.5. And you see, indeed, this nice sequence at all redshifts. So the slope is sort of similar, but you see that the intercept is rising. So the star formation rate at a specific mass is going up with increasing redshift. So as Dan said, this probably says something about the halo inflow rate, the baryonic inflow rate on the halos, and the star formation rate efficiency. And this is the plot that he didn't show, but sort of similar as the one that he showed by Renske, in which you indeed see that if you extrapolate this to high redshift, you see that the specific star formation rate goes up all the way to at least a redshift of 7. Okay, so what can we learn from this? So Peter actually worked on this, and he combined this result with halo merger trees, the mass function, the evolution of the mass function, and the star formation rate history of the universe. And then he tried to say something about the star formation efficiency. I was afraid this plot would take some time to load, but it's there very quickly because it's very big. So what he shows here is halo mass, and this is redshift. And in color coding, you see the star formation efficiency. So this is all being derived from this evolution of the specific star formation rate and all the other observables that we're having together with dark matter halo simulations. And what you see is that the star formation efficiency is actually pretty constant over time, right? And then there's sort of a drop over here. Okay, well, this looks convincing, so are we done? Are we not going to work on this star-forming main sequence anymore in the coming 5 years? Well, actually, I think that the observations still have a lot to improve. Just to give you an example, I think mainly the star formation rates are very, very unreliable. So how are star formation rates nowadays determined? So what people do, since we have this Spitzer telescope, MIPS, they take the UV, they take 24 micron, they have a redshift, they convert a 24 micron to some bolometric luminosity, they have the UV, they combine it together, and they have a star formation rate, right? So UV, IR, obscured star formation, unobscured, combine it together. So what you see here, what we did is we tried whether that actually works. So the new models, the new flexible stellar population synthesis models by Charlie Conroy, some of you may use them, actually have dust emission in them as well. So instead of just taking this empirical way, you can model full SEDs directly. And then we compare the SEDs that you get by modeling the full bolometric energy distribution and just measuring following the UV and the mid-infrared. And if you then divide these two star formation rates or specific star formation rate and compare that to the SED-specific star formation rate, what you see is kind of a systematic effect. And that systematic effect is mainly here at lower star formation rates, and that's because you also actually have UV and IR emission from older stars. They not only come from star formation activity. So you can imagine what that would do to the star formation sequence that may look very tight and suddenly gets blown up a little bit more. So how well can we measure the star formation rate? So this is just one way. There's lots of people who have been trying to improve on this, and there's lots of people who've compared different types of indicators and showed that there may be some problems there. Stellar masses, same story. Although I think this depends a little bit more on what you actually put in. So the stellar masses you obviously get from the light that you observe. So this is a stellar mass function from the work by Danilo Marcassini. And what he did here is he derived the stellar mass function by assuming different kind of by taking different assumptions. For example, what kind of stellar population models am I using? What kind of dust law am I using? What kind of IMF, initial mass function, am I using? And then he derived the stellar mass function, and then he put nice little big boxes around them, and then you see how uncertain this actually is, especially at the high mass end. We don't really know how the mass function looks like. And then all these different properties might actually also change with mass, right? Metallicity probably changes with mass, IMF probably changes with mass, which makes it really complicated to really get accurate mass functions. Okay, so this is from the observational side. So I think we still have a long way to go. And on the theoretical side, so far as I've seen, not many models have been actually successful in reproducing the evolution of the star-forming main sequence. On the other hand, that may not be surprising if our observations are not correct yet. So this is my first question for discussion. If the tight star-forming galaxy main sequence indeed holds up, do we understand why galaxies behave so well for their mass and redshift? So basically, if you know a mass and you know a redshift, and you know it's a star-forming galaxy, you can now sort of predict what the star formation rate is. But is it really that simple? And do we understand this? Okay, second question. How do we actually go from a star-forming galaxy to a quiescent galaxy? So how do we actually shut off that star formation? Kept lots of people busy too, And there were these two popular scenarios. So on one hand, you can think that you can quench a galaxy by having two gas-rich galaxies. They merge together, there's a quasar, and then you get early type galaxies. Obviously, we know the problems with this model is that you can maybe make a galaxy red, but how do you keep it red? Because you will still have gas flowing in onto your halo. So the other very popular theory is the AGN feedback, that you have, for example, this is a more the radio mode AGN, in which you have an AGN in the center that heats up the gas and prevents the star formation. We're going to hear more about that in a talk, I think, in the second session. I think this is a very, very difficult question to address observationally. So obviously, we do see that AGN are doing something to the galaxy. So AGN feedback in action, question mark. That's how I call this slide. So this is work by one of the other organizers, Nadia Sakamska and Jenny Green, who show a radio-quiet obscured quasar with a big outflow of about 1,000 kilometers a second. So there's this other nice example, M87, which we're all familiar with, in which we think we also see this radio mode in action. But to really tie the effect of the AGN to the galaxy itself is really challenging. How do you know what is actually happening and whether what you see is really causal? So how lots of distant galaxy observers like to approach this problem is they take a group of galaxies and then they look at the AGN properties of that galaxy group. So for example, in this work by David Rosario, he looks at the color mass diagrams. He plots all the galaxies and he plots the AGNs and tries to understand in what types of galaxies do you actually find the AGN. So it may not be apparent from this plot, but if you really control the samples really well, he actually finds that the AGN are stronger in star-forming galaxies and not in quiescent galaxies. Other groups say, no, they're stronger in quiescent galaxies, and other people say, no, you find them in the green valley, which is this transitional zone between what we call the blue cloud here and the red sequence over there. So there's definitely no consensus there, but then even if you find, like where you find them more, how do you know that the AGN are doing something, right? Maybe they're just feeded from the same gas supply in the system. So we did a similar analysis using X-ray stacking, and we looked at the X-ray luminosity as a function of the age of the population. So this is D4000, that's a measure of the age of the population. And we find a similar thing as David Rosario did, that the AGN activity, or the X-ray flux, is higher in star-forming galaxies than in galaxies that have older stellar populations. So there's also quite a lot of theoretical work. So the way how AGNs are put into big hydrodynamical simulations may not be very physical, but people are actually trying to model this in detail. And this is from current work by Claude André and Elliot. So Elliot can probably tell us more about this during discussion session, but they actually find that this AGN feedback may actually be more effective than initially thought. Okay, so these are my questions regarding this point. Clearly, we're not done here yet. So some groups actually claim, or some theorists actually claim, we don't actually need AGN feedback at all. So that's my first question, AGN feedback, do we need it? And if yes, does it work? Can it actually work? And the other question I want to ask is, what can observers do? So how can you really observationally address this? How can you really make the connection between the AGN properties and the galaxy properties? Okay, so the last topic I want to talk about is the growth of the quiescent galaxies. So this kept people busy from around 2008, 2007. So here you see a compilation of a lot of different works about the size evolution of elliptical galaxies. So what you're seeing here is the size normalized to a redshift of 0 versus the redshift. And what we're finding that at fixed stellar mass, quiescent galaxies were about a factor 4 to 5 smaller at a redshift of 2 than they are today. So when this was initially discovered, people said, no, you're doing something wrong. You're just not measuring this right, because this cannot be right. But it is right. It is measured well. So if you, for example, here look at the profile of such a galaxy, and this is done with the WIFC-3 camera on HST, which just came available at the time we're starting discovering these things, and it was much deeper than the previous camera, so we could really confirm that these galaxies were indeed much more compact. So here you see one of those redshift 2 galaxies compared to Virgo galaxies, and you indeed see that the shape, the profile is really different. It's not that we're only seeing the middle of the galaxy and that's why they look smaller. No, these galaxies are really smaller. Okay, so maybe the sizes are correct, but I already told you masses are really hard to measure, so maybe the masses are just incorrect, right? Well, we try to measure the masses using an independent approach, so not actually measuring photometric masses, but dynamical masses by getting the stellar velocity dispersion. This is kind of a hard work at a redshift of 2 because the lines from which you want to measure the velocity dispersion have been shifted to the near-infrared, and it's very difficult to take near-infrared deep spectra of these very, very distant galaxies. But we're getting there, and we now have, there's actually 5 red points, they sort of overlap. We have about now 6 galaxies around a redshift of 2 for which we can get a dynamical mass, and if you compare the dynamical mass with the stellar masses, they're actually pretty consistent. So what you see are a lot of other works as well. So the gray is Sloan, so galaxies in the local universe, and there's a lot of other works varying between the redshift of like 0.8 up to 2. And all these works actually show that the photometric masses are actually pretty good. Okay, so these galaxies are really compact. And you indeed see, if you look at the evolution of the velocity dispersion, that the velocity dispersion, so the density, the stellar densities in these galaxies were indeed higher at earlier times. So here you see the velocity dispersions versus the dynamical mass, Sloan and all these more distant galaxy samples. And here you see, if you take out this slope, how it looks like as a function of redshift. And you see that the velocity dispersions were quite a bit higher at earlier times. Okay, so I've been talking about comparing at similar mass the whole time. I'm looking at radii of galaxies at the same mass. But that's not fair, right? How do we know that these galaxies really evolve into each other? So you want to match galaxies at different redshifts that actually are probably progenitors and descendants of each other. So what we've been using is a different approach, and multiple people have been using this in the past year, and that's actually selecting galaxies at a fixed number density. So what you're seeing in this plot are sort of tilted mass functions. So you have here mass, you have number densities, and so basically, if you have star formation, you would move galaxies up into this direction. So you don't make galaxies, you don't get more galaxies, no, you just make galaxies bigger. That's the same what happens if you have mergers, minor mergers especially. So you don't make more galaxies, no, you change this m, you don't change this n. Only major mergers is sort of a problem in this scenario. But the idea is, if you select galaxies at a fixed number density, so at a fixed n, you're actually looking at the same galaxies at different redshifts. That's the assumption. So now I say, okay, I'm going to select at a fixed number density. At this number density, I have galaxies of this mass. At this number density, at the same number density, they have this mass. So I now take galaxies of a specific mass or a mass slice at time, and then I start comparing them with each other. And then you can see how galaxies that are supposed to be the same at different redshifts actually evolve. And what you're looking at here is how the surface brightness profiles evolve over time. So these are different scales. The one is linear, the other one is log. So it doesn't really matter which you look. But the idea is that this is redshift 2, and red is redshift 0, that galaxies really build inside out. So they first build their core, and later on, they build their outskirts. So these compact galaxies that we see at early times are the cores of the big elliptical galaxies we see today. So what's doing this? So what is causing this growth? It's inside out. So if you look at the evolution in both RE, in both size, effective radius, and mass, you find that it's going in this direction. And this is actually consistent with merging with smaller galaxies. So if you have merging with bigger galaxies, so major merger, you would get this vector. So R goes proportional with m, but minor mergers is more R goes proportional to m squared. And you see that's sort of the direction we're going. So these galaxies are probably building up by minor mergers. Okay, is it that simple? Minor mergers puffing it up, so question solved. Well, this is indirect, right? We're thinking that it's minor mergers, but we don't actually count the minor mergers. So this is what this work by Drew Newman shows, is if you actually count the minor mergers, that this idea might actually be problematic. So this is what you expect in evolution based on mergers. We all know that it's like by just doing pair statistics is actually really difficult to go from pair statistics to a merger rate. There's lots of assumptions going in there, but even with different assumptions, he cannot explain the very rapid size evolution we see at early times. So is there still a problem there? Well, it seems like it. Okay, so what are other ways to make galaxies go bigger over time? So one thing you can think about is that the population is also growing over time. So galaxies are still transforming from a star-forming galaxy to a quiescent galaxy. So maybe the galaxies that quench or that transform at later times, they may be bigger, and because they're bigger, they will become bigger elliptical galaxies, and they will make the general population of elliptical galaxies bigger, right? So that could also be a way to make the galaxy population grow bigger. So this is something we looked at as well, and we split the quiescent galaxies into the old and the young quiescent galaxies and looked at their size. And we found that young and old quiescent galaxies are all about the same size. So basically, the young quiescent galaxies are as small as the old quiescent galaxies, which means that adding bigger quiescent galaxies is not the reason how we can explain the size growth. So there may still be an issue here. Okay, I'm going to skip this one. So I want to end with my question slide concerning this topic. Okay, so the first question, is there still a problem with the minor merger scenario? Can they indeed explain the size growth of elliptical galaxies or not? Do we just have to do the test again? Do we have to do the counting again? Or is there really a problem there? The other question is, how are these compact quiescent galaxies formed in first place? So that's connected to the previous question about how do we go from these blue galaxies to these red galaxies. And one thing that I actually skipped, but may be interesting to show very quickly, a lot of these quiescent galaxies, these compact quiescent things at early times, are not actually real elliptical galaxies. They seem to be disky. They might actually be disks, although this still has to be confirmed. Okay, and the last question is, how well does this constant number density selection actually works? And that's probably also a question for Peter, who wrote a paper about that as well in the last year. So that's where I want to end. Thank you.
The size distribution results are still a little suspicious just because the dynamic range is so enormous. The difference in dynamic range, like the measurements are being made with different instrumentation and different pixel scales and different exposure times and different signals noise, different source density, different importance of confusing stars. I mean, there's a lot of differences being made.
Yeah.
One thing I'd be interested to know, but it's too detailed a question, I guess, is how much room there is in the measurements at the faint levels. For instance, sky, for instance, is always a problem with galaxy size. In fact, all of Sloan's sizes were wrong for several data releases. And I don't think anybody's really decided what the right way to determine the sky is. And it'll be different for the different. Anyway, that's not really a question, but you know what
no, I agree. And I think there's definitely, it's probably not a factor of 2 effect, but it might be 20% effect. I do think there's still a problem there. And also, how much are you still missing, right? Yeah. But it's not as big as people initially thought. And it's not as big as to explain that there is no size evolution at all. So there's definitely size evolution, but maybe a little bit is due to the effects you're talking about.
This is a very naive question, but I'm just wondering, with the mass size relation, how does the size of the effect that you measure compare to the size of the effect that you would expect just naturally from virialization arguments. You would expect there to be an h of z term that naturally comes into that relationship, which would have the same direction as the effect that you're showing.
So the size, if you look at the velocity dispersions we're measuring, the sizes and the masses, it's all consistent. So based on like how they're very compact, they're massive, and we indeed find higher velocity dispersions. So these galaxies, as you saw, the dynamical masses were consistent with the photometric masses, which immediately says that it's all consistent.